For decades, black holes seemed like the final limit of cosmic violence. Nothing could escape them. Nothing could compete with them. Nothing could survive them. But on August 17, 2017, two observatories on opposite sides of the planet, LIGO in the United States and Virgo in Italy, detected a ripple in the fabric of space-time. It was not a black hole. It was something smaller, stranger, and in many ways more violent. Two neutron stars, the densest objects in the universe that are not black holes, had collided. And what we learned from that single event changed everything we thought we knew about how the universe builds its heaviest elements. We start with the sheer physics of these objects, because the numbers are almost impossible to hold in your mind. A neutron star begins its life as a massive star, often many times the mass of our sun. When that star exhausts its fuel, its core collapses. Gravity, the same force that keeps your feet on the ground, crushes the stellar core into a sphere only about 20 kilometers across. A city-sized corpse made from the remains of a star. Imagine a teaspoon of matter so dense it weighs as much as a mountain. A sugar cube-sized piece of neutron star material could weigh hundreds of millions to billions of tons. That is not poetry. That is physics pushed almost to its breaking point. But density alone is not what makes these objects terrifying. It is what that density does to gravity. On the surface of a neutron star, gravity can be hundreds of billions of times stronger than what we experience on Earth. If you somehow reach that surface, and let us be clear, you would not survive for even a fraction of a second. You would not stand. You would be crushed, flattened, torn apart by gravity and tidal forces before your nervous system could even register pain. The human body does not belong there. No chemistry does. No structure built from ordinary matter can remain human under that kind of force. And yet the surface is only the beginning. For decades, we pictured neutron stars as relatively simple monsters. A solid crust, a sea of neutrons, and perhaps a superfluid interior where matter flows with almost no resistance. A superfluid is a liquid with nearly zero viscosity, meaning it can flow without losing energy in the ordinary way. Imagine stirring a cup of coffee and watching the swirl refuse to die, not for seconds, not for minutes, but for years, centuries, maybe longer. That is the kind of impossible behavior physics allows inside these dead stars. But recent observations, including measurements from NASA's NICER instrument on the International Space Station, have made the interior mystery even deeper. The core of a neutron star may not be made of ordinary neutron matter at all. Under pressures this extreme, neutrons may deform, dissolve, or give way to exotic phases of matter, possibly even matter where quarks are no longer locked inside individual particles. We do not know for certain, and that uncertainty is the terror. A true quark-gluon plasma existed in the first moments after the Big Bang, and can be recreated for tiny fractions of a second in particle accelerators. But if anything similar hides inside neutron stars, then these dead stars are not just graves of collapsed suns. They are laboratories where matter is pushed to the edge of what physics can describe. But before we go deeper into what hides inside these objects, consider this. Of all the violent phenomena in the cosmos, from supernovae to black hole mergers, the collision of two neutron stars produces something that may be touching your skin right now. And that is where the story becomes personal. Here is the question that kept astrophysicists awake for decades. Where does gold come from? We knew the Big Bang produced mostly hydrogen and helium, with tiny traces of lithium. We knew stars could fuse elements in their cores, hydrogen into helium, helium into carbon, carbon into oxygen. And eventually, in the most massive stars, fusion can build elements up to iron. But the heaviest elements, gold, platinum, uranium, and many of the rare earth metals inside modern technology, require something far more extreme than an ordinary stellar core. The math simply does not work. You cannot build gold by calmly fusing iron inside a normal star. The energy demands become too high. The conditions are wrong. So for decades, the origin of many of the universe's heaviest elements remained one of the great unsolved mysteries of astrophysics. The answer came from that August morning in 2017. When two neutron stars spiral into each other, their mutual gravity distorts them before they merge. Tidal forces pull at their crusts. Matter is ripped away. The stars whip around each other faster and faster until, in the final moments, they collide in one of the most violent events the universe can produce. The explosion that follows is called a kilonova, not a supernova. Not a nova. A kilonova, a cosmic forge born from dead stars. For a brief moment, the collision releases an enormous burst of light, gravitational waves, high-energy radiation, and newly forged matter into space. Inside that fireball, conditions become so extreme that neutrons bombard atomic nuclei at unimaginable rates. This is the rapid neutron capture process, the R process. It is one of the universe's great factories for heavy elements: gold, platinum, uranium, rare earth metals. In a single neutron star merger, staggering amounts of heavy material can be created. In the case of the 2017 event, estimates suggest that enormous quantities of heavy R process elements formed, including several Earth masses of gold and platinum combined. That means the gold in your ring may not be ordinary metal at all. It may be the frozen ash of two dead stars colliding. Think about what that means. The gold in jewelry, the platinum in catalytic converters, the uranium that powers nuclear reactors, the rare elements inside phones, satellites, and medical scanners. Some of those atoms may have been forged in a collision between two dead stars, billions of years ago, long before Earth existed. We are not separate from the cosmos. We are made of it. And some of our most treasured materials were born in its most violent moments. But neutron stars are not just factories for heavy elements. In isolation, they become something equally extraordinary. Many neutron stars rotate at staggering speeds. Some spin hundreds of times per second. As they rotate, they emit beams of radiation from their magnetic poles. Those beams sweep across space like the light from a lighthouse. And when one of those beams points toward Earth, we detect a pulse. We call these objects pulsars, and they are among the most precise natural clocks in the known universe. The best millisecond pulsars are so stable that over long timescales, their timing can rival some of the most precise clocks humans have built. We use them to test Einstein's theory of general relativity. We use them to study extreme gravity. We use networks of them to search for gravitational waves too faint and slow for detectors like LIGO to catch. A dead star, spinning in the dark, can become a clock for the universe. And then there are magnetars. If a neutron star is born with an unusually strong magnetic field, it becomes something even more disturbing. A magnetar. Its magnetic field can be a quadrillion times stronger than Earth's. Close enough that field would not simply pull on metal, it would distort atoms, disrupt chemistry, tear matter apart at the electromagnetic level. A magnetar is not just a dead star, it is a magnetic weapon forged by gravity, and occasionally magnetars crack. Their crust shifts in a starquake, releasing a burst of energy so violent that for a fraction of a second, one dead star can outshine almost everything around it. On December 27, 2004, a giant flare from the magnetar SGR 180620 reached Earth from tens of thousands of light-years away. Even across that distance, the radiation disturbed Earth's upper atmosphere and left a detectable signature in the near-Earth magnetic environment. A dead star, alone in the void, touched our planet from across the galaxy. We have spent this journey looking outward at these objects, cataloging their extremes, their density, their gravity, their rotation, their magnetic fields, their collisions. But the deeper truth is this: neutron stars are not distant curiosities, they are architects of the periodic table. Without neutron star mergers and other extreme R process events, the universe would be missing much of its gold, platinum, uranium, and many of its heaviest elements. Without supernovae, the explosions that can give birth to neutron stars, there would be no carbon, no oxygen, no iron in the forms that made planets and life possible. Most of the elements heavier than hydrogen and helium were forged inside stars, in stellar explosions or in the collisions of stellar remnants. The calcium in your bones, the iron in your blood, the oxygen in your lungs, the carbon in every cell of your body. Every atom carries a history older than Earth. Some were born inside stars, some were scattered by supernovae. Some may have been forged when two neutron stars collided and tore space-time itself into waves. We are, in the most literal sense possible, the children of dead stars. So the next time you hold a piece of gold, or feel the weight of your own body, remember where it came from. Not just from Earth, not from something ordinary, but from stellar furnaces, from supernova fire, from dead stars spiraling together in the dark, from the most violent, most precise, most magnetic objects in the known universe. Neutron stars. If this journey through the extremes of physics meant something to you, subscribe and join us as we explore the infinite depths of the cosmos together.